This video lesson is about the fundamental theorems of calculus, which are the central idea that links the two operations in calculus, namely differentiation and integration. To set up a good mood in this lesson, let us consider these illustrations. The two main operations in calculus are differentiation, taking the derivatives, and integration, which are computing integrals. Each of these operations has their own motivation and application. For example, the operation differentiation mainly is about slopes of tangent lines. On the figure on the left, you can consider the yellow curve or the yellow function, and in performing differentiations, we are usually interested to calculate the slope of the tangent line depicted by the blue line in the picture. Normally, the slope of the blue line cannot be calculated directly without relying on a limiting operation. What we do is we approximate the slope of the blue line by considering the slope of the red broken line. As you can see, the slope of the red broken line is given by the formula rise over run, or delta y divided by delta x. Okay, and as you can see, as delta x gets smaller and smaller, or as delta x approaches 0, the slope of the red broken line approaches the slope of the blue line. On the other hand, the operation integration is about getting areas under a curve. Let us consider the same curve, but this time our problem is to calculate the area, shaded as shown. Notice that the area cannot be calculated directly without using a limiting operation, as the yellow boundary is a curve. No? What we do is we approximate the area by rectangles, and in this case we can say that the product delta x times delta y, which is the area of the rectangle, the white rectangle, is approximately equal to the area under the curve, this being the error of the approximation, and that error goes to 0 as delta x approaches 0. So basically, what we can observe is that getting slopes of tangent lines involves division, while getting areas under curves are basically obtained using multiplication. Now, because division and multiplications are inverse operations, it is not surprising that the operation differentiation and integration are also inverse operation in some sense. This lesson reveals that inverse relationship between differentiation and integration. The two fundamental theorems of calculus reveals or formalizes the inverse relationship between differentiation and integration, as we shall see. So without further discussion, let's state the first fundamental theorem, or actually one of the fundamental theorems. It doesn't matter which one is first or second, as long as you know that there are two. Okay, so the first fundamental theorem of calculus in our class is this, and this is one of the more, let me say, famous than the other, because this is actually a formula that students in calculus use in order to calculate some integrals or definite integrals. So it says that if you have an integrable function f on the closed interval ab, and if you know that this function f has some antiderivative big F, What do you mean by an antiderivative? It's a function whose derivative is little f. So in elementary calculus, you have learned how to get antiderivatives, right? So being an antiderivative, we mean to say that the derivative of big F is the little f, and this equation holds for all x in the interval AB. So once you have found an antiderivative for little f, namely big F, then the integral can be calculated by evaluating the antiderivative at the right endpoint B minus the value of the antiderivative at the left endpoint A. As we can recall from elementary calculus, there is a shorthand for the expression big F of B minus capital F of A. It's usually denoted using this bar notation, right? In the proof of this theorem, we will be needing the mean value theorem for derivatives, stated as follows. It says that if f is continuous on the closed interval AB and differentiable on the open interval starting from A ending at B, then one can always guarantee that a number C between A and B can be selected so that the derivative at C of f equals this quantity. As you can remember from advanced calculus, if I remember it correctly, let's say this is your function, alright? So let's say this is A and this is B. So this is f of A and this one is f of B. So in this case, the function f is continuous on the closed interval AB as illustrated and differentiable. It doesn't do sharp turns between A and B. So as you can see, the quantity on the left hand side of the equation, namely this one, is basically the slope of this line segment. Okay, the slope of this line segment is f of B minus f of A divided by B minus A. According to the mean value theorem, at some value C in between A and B, I think in this case it is this C, or maybe here. I think the C that we are looking for is this, because the tangent line, I think derivative now, the tangent line at that point, sorry, let me make my tangent line, yeah, so the tangent line at this point has the same slope as this fixed line segment. Or you can imagine that if you try to move the tangent lines from A to B, at some point in between the tangent line will be parallel to, because equal slopes means the lines are parallel, right? So anyway, so this is the mean value theorem, and this is one of the key ingredients enable for us to prove the fundamental theorem of calculus, the first fundamental theorem of calculus. So let us begin the proof, and we will do it step by step. So let us suppose that f has an antiderivative, big F is an antiderivative of little f on the interval AB. So its existence is assumed, or assumed by default. We would like to show that the integral of little f from A to B is equal to big F at B minus the value of big F at A. So what we do is we consider an arbitrary partition of the interval AB, namely P. Now, for each of the n subinterval, so we will consider every subinterval now. So you can see, because big F is differentiable by default because its derivative is little f, right? So it's differential by default on the interval AB. Differentiability implies continuity, so we can guarantee that big F is continuous on every subinterval, and of course differentiable on every subinterval. Here is where we are going to apply the mean value theorem. Because F is continuous on the closed and differentiable on the open, by the mean value theorem for each k, we can find a number c sub k between xk minus 1 and xk, so that this is true. Alright, so as you can see, this is just the other version of the mean value theorem. Doon sa aking sinulat sa naunang slide, itong quantity na to was just written here. Tapos, ito wala yan doon. Ay, ganun yung nandoon sa nasa previous na slide, and then nire-write ko lang, no? Now, again, because big F is an antiderivative of little f, the derivative of little f is little f at every point in this interval. Therefore, this derivative f prime of c sub k is equal to little f of c sub k, and as you can remember, this quantity is denoted by delta xk. This is the length of the kth sub interval. Okay? Now, recall that for each k, yung little mk, ito yung infimum ng f sa kth subinterval. Ito yung supremum ng f on the kth subinterval. Therefore, if ck is any point in that interval, the value of f at ck will be between the infimum and the supremum, right? Now, summing all of this up, k from 1 to n, and multiplying each one by delta xk, if we multiply each member of the inequality by delta xk and summing them up, k from 1 to n, we will get the inequality as shown, or labeled inequality number 1, that the lower Riemann sum with respect to p and the upper Riemann sum with respect to p bounds in below and above the sum, as you can see. Again, how did we able to come up with this? We multiplied delta xk to each member of the inequality, okay, and then we sum them up. Dito ko na lang susulat, k from 1 to n. If we do so, itong sum neto magiging lower Riemann sum. Yung sum naman neto magiging upper Riemann sum, right? That's why we have the following inequality. Now, what I wanted you to do is to look at this. Okay. As you can see, by the mean value theorem, or by this equation, I could replace f of ck delta xk by big F of xk minus big F of xk minus 1. That's why this sum can be rewritten as follows, right? So, what we do is we now expand this summation. When k is 0, what will happen? K is 1. This is f of x1 minus f of x0. When k is 2, this is f of x2 minus f of x1, and so on. When k is n, this is big F of xn minus big F of xn minus 1. As we can see in this sum, this is actually a telescoping sum. When you say telescoping, magka-cancel yung maraming terms. For example, itong dalawa, magka-cancel like so. Itong f of x2, magka-cancel yan doon. Anyway, meron lamang dalawang, when you try to expand this, meron lamang dalawang terms na may iwanan. And the terms that will remain are this one and this one. In that case, f of xn minus f of x naught, remember that in a partition P, yung xn siya yung B, yung x naught siya yung A. Right? So therefore, using inequality number 1, we can say that ito yung summation, right? F of b, this constant f of b minus f of a is always between LFP and UFP. But as you can see, the partition P is, well, arbitrary. Therefore, if you take the supremum of this, it will not exceed this constant. And if you take the infimum of all of this, you will not go below this constant. Therefore, we have the following. This is the lower Riemann integral and the upper Riemann integral. But as given, f is Riemann integrable. Therefore, these two quantities are actually equal. And if that happens, it meant to say that these three members of the inequality are actually equal. And their common value is f of b minus f of a. As a conclusion, if you integrate little f from a to b, ito yung common value ng LF tsaka yung UF, which is f of b minus f of a. And now we have proven the first fundamental theorem. So, for example, if big F is x squared plus 2x, so its derivative is, let its derivative be little f of x, which is 2x plus 2. So if one wants to integrate 2x plus 2 from 0 to 1, let's say, then you can get this by evaluating big F at 1 minus big F at 0, namely 3 minus 0, or 3. So there is no need for us to go back again to the definition, yung mga summations na mahihirap in order to calculate integrals. No? As long as you know how to get an antiderivative for a function, walang mahirap sa pagkuha ng integral or sa pagkakalculate ng integral. Now, one consequence of the first fundamental theorem is what we sometimes call in the business as the integration by parts. Paano naging integration by parts ito? No? So let's see. So let f and g be differentiable functions so that their derivatives are integrable on the interval ab. Now, in calculus, for most of the interesting cases, kapag ang function differentiable, karaniwan, ang derivatives naman ay integrable. Napaka-rare mangyari na ang derivative ng differentiable function ay hindi integrable. Well, that can happen, maybe, but for most of the interesting cases, this is almost guaranteed. Then, according to the theorem, this integral, as you can see, ito yung f times derivative ni g, derivative ni f times g, so it reminds you of something, right? Is f of b times g of b minus f of a times g of a. Let us see why. It is based on the, what do you call this? The product rule for differentiation. You know that the derivative of f of x times g of x is this. Right? So, if you wanted to integrate this derivative from a to b, then what do we do by the first fundamental theorem? You simply evaluate the antiderivative at b minus the antiderivative at a. That's it. Why is this the integration by parts? Kasi using linearity and some algebraic manipulations, itong integral na to can be made into 2. And then, yeah. So, yung unang integral dito, ito siya. Okay? Yung integral na to, nilipat ko siya doon. And then, yung quantity na to, yun yung f of x, g of x evaluated from a to b. So, ito na yung, I think, yung mas familiar na form sa inyo. Ito yung u dv, uv, tapos ito yung v du. Right? Okay. So for example, we wanted to evaluate the integral of x cosine x dx from 0 to pi. So apply kang formula, mag-iisip ka ng u at saka dv dito, di ba? Or u and v. So dito parang ang u mo naturally dapat, di ba, yung x. Ang dv mo naman yung cosine x dx. So ano yung v nun kung ito yung dv? Ang v mo nun ay sin x. Ito yung u. Of course, these examples are just made to illustrate the theorem, but in reality, in this subject, we will not be calculating integrals because that is not our business here. Our business in this subject is to explain the theorems and the underlying proofs, which you skipped out when you were in elementary calculus courses. So if we apply the integration by parts formula, that's it. And then you're left with the integral from 0 to pi ng sin x dx, wherein, in this case, pwede natin i-apply yung first fundamental theorem once again. We know that minus cosine x is an antiderivative for sin x. Therefore, we have the following. And the final answer is negative 2. Okay? Now, in order to state the second fundamental theorems, there will be just some conventions that we're going to use, and it will be helpful to patch up some loopholes in the proofs. Okay? So, if f is integrable in the interval ab, remember, ang integral natin always goes from a to b. Paano kung yung integral mo goes from c to c? Sorry, the interval only has one point in it, no? So in this case, we simply define the integral to be 0. Well, this is a definition, so we don't need to explain, but this is quite intuitive because if let's say this is your function and this is your point c, if we don't move at c, may area ka ba na masaswipe? Wala. So parang intuitively, that's the idea of the number or the integral 0. On the other hand, sanay na sanay tayo mag-integrate from a to b where a is less than b. Right? Paano kapag meron tayong integral from, let's say, 3 to 1? Nag-start ka sa something bigger, tapos natapos ka sa something smaller. Now, of course, that doesn't make sense, but for the sake of a good convention, if a is less than b, we define the integral from b to a as the negative of the integral from a to b, because this now makes sense. If we define this to be this one, magma-make sense na rin siya as a consequence. Now, because of these conventions, naalala niyo yung additive property that if this is your function, this is a, this is c, this is b, in this order, then the integral from a to c plus the integral from c to b equals the integral from a to b. It can be shown using these conventions that whatever the order of a, b, and c are, pwedeng, let's say, ito yung a, b, c, let's say, yung additive property natin ay nag-work pa rin. I mean, tama pa rin yung integral from a to c plus integral from c to b equals the integral from a to b. In this case, why? Kasi yung integral na ito, yung mula dito hanggang doon, magka-cancel with this. Remember, pag bumabalik ka, nagne-negative yung sign. Kaya may iwanan na lang ito. So this is the logic. So the additive property can be applied, regardless of the order of a, b, and c, as long as they are all in an interval where f is integrable. Did you understand? Okay. Here, we are defining the word indefinite integral. Now, this might confuse you because in elementary calculus, I think the word indefinite integral definite integral, or antiderivative. You confuse these three. You think that these three are of the same thing. But technically, no. Yung integral natin from a to b is sometimes called as the definite integral from a to b. Kapag sinabi natin indefinite integral, indefinite kasi look at the rightmost limit of the integral, or the right limit of the integral. X variable. So, kaya nga indefinite kasi if x is variable, the right endpoint can move, right? Hindi siya fixed. Kaya yung value na integral mo varies as x varies. That's why this integral is called a definite integral. Take note that here I am using another variable. I'm using t because yung x ay nagamit ko dito. So para hindi lang magkaroon ng clashing of variables, I used a different variable for little f. Okay? To illustrate what the indefinite integral of f is, this is wrong. I think may correction dito. Dito f. This is if. Okay? I symbolize it as if. Okay? So, to illustrate, remember, ang integral ay, well, kung continuous yung function mo, parang area yan, right? So, looking at the picture, ito yung little f, ipa-plot ko dito yung graph ng if as x changes from, or as x moves from a to b. Of course, by the way, if x is a, ang if of a is the integral from a to a, so that is going to be 0. So 0 siya, dito siya mag-i-start. But as x moves from a to b, this is what will happen. It's like, ayan, nakikita nyo, no? As x goes to the right, from a to b, naiipon yung area mo from A going to B. So, it's like ang trabaho ng if ay mag-accumulate ng area under the curve from A. Do you understand? So, that's what usually happens. So, yung indefinite integral mo is another function. Okay? Ulit, ang definite integral ay number, ang indefinite integral ay function. Function that tells you the accumulated area from the left endpoint up to some point before the right endpoint. Is that clear? Okay. In fact, the second fundamental theorem is about this indefinite integral. It tells us that, alright, so this is the statement. If little f is integrable, then yung indefinite integral daw ni f, which is defined as shown, nakita niyo yan in the previous slide, is going to be continuous. In fact, dahil ito'y closed interval, siya ay uniformly continuous. Ulit, kapag ang function ay integrable, automatic, so kahit na hindi ito continuous at all, basta siya ay integrable, automatic, pag kinaw ni indefinite integral niya, the indefinite integral will be continuous, or furthermore, uniformly continuous. Eh, paano sir kung ito ay continuous? Well, nag-upgrade din yung quality. If little f now is continuous, the indefinite integral now is going to be differentiable. Okay, on the open interval from a to b. Ulit. Pag ang function ay integrable, yung indefinite integral niya ay continuous. Kung yung function ay continuous, yung indefinite integral niya ay differentiable. Parang, imagine niyo, remember may Venn diagram tayo ng mga functions na. Parang nandito yung mga continuous, nandito yung mga differentiable, kasi lahat ng differentiable ay continuous. Tapos, nandito yung mga integrable, kasi lahat naman ng mga continuous ay integrable, right? So kapag yung yung little f mo ay nandito, integrable siya, yung if mo pumapasok dun sa next class higher. Okay? Kung yung little f mo naman ay naririto, yung ano mo, yung indefinite integral mo, pumapasok dun sa susunod na set or sa stricter na set. Okay? Do you understand? So parang it's like saying that taking the indefinite integral improves the quality of the function. Okay. So again, if little f is continuous, the indefinite integral if is going to be differentiable, and therefore ano kaya yung derivative niya? Kasi kapag differentiable, it meant to say that it has a derivative. So, surprisingly, or I mean, you may not be surprised at all, ang derivative ng indefinite integral mo ay yung little f ulit. So, meaning to say, if you do integration for a function f that is continuous, it gives you a function whose derivative is little f. So, parang nagbabaligtaran lang. So, ito na nga yung sinasabi natin, ang integration at saka differentiation ay parang reverse operations, because if you differentiated what you have integrated, there's nothing that really happens. So, as you can observe, yung second fundamental theorem is like taking derivatives of integrals or indefinite integrals for that matter. On the other hand, yung first fundamental theorem, you are integrating a derivative. You see the cancelling effect, no? Because they are inverse operations, they normally would cancel if you do one after the other. So that's the idea. That's why we sometimes say that differentiation and integration are inverse operations. So to prove, we start by assuming that f is integrable. Now we all know that before a function to become integrable, it has to be bounded first, because we do not allow unbounded functions in our discussion of Riemann integrability, right? So if f is integrable, then it must be bounded, and by bounded we mean we can find a positive number m so that yung magnitudes ng f of x can be bounded by some number m, no? And this should happen all throughout the interval from a to b. Okay. To show that if, or the indefinite integral, is uniformly continuous on AB, we let an epsilon be greater than 0. Ano nga yung uniformly continuous? Let's recall. So if is uniformly continuous on AB if and only if, ating definition, for every epsilon greater than 0, there exists a delta greater than 0, such that the images of any two things, let's say S and T, the images of any two things S and T will be less than epsilon as long as these numbers S and T is chosen in the domain, and their distance is less than delta. So this is what we mean by a function. This is f. Ano ba? Kunwari si f na lang, little f na lang. Pero in our proof, we are going to show that if, or the indefinite integral, is uniformly continuous. Kaya nga ang proof ng uniform continuity will always begin with let epsilon be greater than 0. Ang karugtong niyan, we are going to find the delta greater than 0, so that whenever these things hold, whenever S and T are near, yan sa English yan, no? Then their images are also near. So it's like saying that uniformly continuous function preserves nearness. Okay? So how do we get a delta? So first, observe that if you pick any two numbers, u and v, in the interval a, b, Then, if we do if of u minus if of v, because remember, ito yung plano natin gawing less than epsilon, no? Ano kaya yung delta? Anyway, let's compute. By definition, ito yung definition ng if. Ini-integrate mo from a to u, yung little f. Ito naman, ini-integrate mo from a to v, yung little f, like so. So, we have this. Ang gagawin ko dito, i-apply ko yung additive property. So, paano yun? I would like to change this to a positive sign first by swapping this limit. So, magkakaroon ako bali ng integral from a to u plus integral from v to a. So, now I have an integral from v to a plus integral from a to u. All in all, it can be summarized into one integral from v to u, like so. Now, I'm going to use at this point the triangle inequality for integrals. Do you remember that? That the absolute value of the integral is less than or equal to the integral of the absolute value, like so. In our case, f of x for all x has an absolute value less than or equal to m. So, by monotonicity, this integral before going there, like this, is less than or equal to m times dt. If we evaluate this integral, this is m times v minus u, right? But remember, u and v can be in any order. This quantity is non-negative because of the absolute value. So, to ensure that the inequality holds, lalagyan ko ng absolute value ito. Kasi it simply measures the length of the interval. That's why ito naging ganyan. Okay? Non-negative kasi ito. Tandaan niyo yung bound na ito, ha? Gagamitin ko siya. So, if we want this to be less than epsilon, how do you choose the delta? Remember, ito yung less than delta. So, if this one is the one less than delta, if you want this to be epsilon or less than epsilon, how do you choose your delta? We should choose it so that delta is at least or at most epsilon over m para mag-cancel yung m. Kaya nga sa next na step, we let delta to be epsilon over m. If now two numbers u and v have distance less than delta, which is epsilon over m, this is what will happen. According to our estimate a while ago, this is less than or equal to m times absolute u minus v, and this is less than m delta. And in this case, our delta is this, so magiging less than epsilon, achieving our goal. So therefore, we have proven that f is uniformly continuous on AB. By the way, uniform continuity implies continuity as well. It's a stronger form of continuity. So, what we have accomplished so far, na-accomplish natin that if f is integrable, yung indefinite integral ay uniformly continuous on the interval of integration. Next, we now assume that f is continuous. We would like to show now that the indefinite integral will be differentiable, and we would like to prove that its derivative is little f at every point x in the interval ab, like stated, like so. Now, paano magkakatotoo yan? So, ang derivative ni if ay si little f if and only if the following limit holds. This was taken from the definition of derivatives, right? Sometimes we use delta x. Okay, so how do we prove this for an arbitrary x? So this is what we do. We take an arbitrary x in the interval AB, and because h will approach 0, so we may assume that h is not 0. But this h will be selected so that yung x plus h, gusto ko yung x plus h nandun pa rin sa domain. Okay? Kasi i-evaluate natin, may mali na naman ako dito, ay dapat ito, kasi dun sa lecture notes nyo I used big F yata, but in the slides I used IF. Copy paste, sorry, tao lang. So because I am going to evaluate IF at x plus h, so I need to ensure that h is small enough so that x plus h is still in the interval from a to b. It's like, halimbawa, ito yung interval from a to b, right? Kung dito mo pinili yung x, yung h, wag mong pipiliing malaki. Kailangan yung x plus h hindi lumalabas doon sa interval. Okay? Okay, bakit naging ganyan yan? Ulit, ito yung IF. O basta, yung kapag may nakita kayong big F dyan, I only mean IF. Okay? Now, yung 1 over h, nilabas ko muna. Yung IF of x plus h is this. Yung IF of x is this. And then, katulad kanina, papalitan ko ng plus to. Pagpapalitan ko yung limits na ito. So, maging x from x to a to x plus h. If you combine them together, it can be summarized as such. Okay? Tama? Next. I want you to look at this. This is very tricky at first. Sa unang tingin, mahirap itong makita. Pero nakita nyo, we are integrating with respect to t. So, it's like saying that yung f of x dito ay constant. So, pwede mong ilabas yan doon. Pag lumabas siya doon, so you have f of x over h, integral ng dt from x to x plus h, matitira na lang h, magka-cancel yung h na to doon sa h na yon. Ang matitira yung nilabas mong f of x, kaya nga sila ay equal. Now, why would I want that? Now, remember, ang goal ko is to prove that the limit of this as h approaches 0 is equal to this. Okay? So, ang gagawin ko kasi isusubtract ko silang dalawa. At dahil isusubtract ko silang dalawa, gusto ko silang gawing magkamukha. So, the subtraction can be written, or the difference can be made beautiful or nice. Let's see. So, biglang naging IF na, no? Basta yung big F dito sa taas, IF talaga yun, ha? Okay. Isusubtract ko na nga ito. Kasi gusto kong ipakita na ito'y lumiliit as h approaches 0. So, I need to know how big is this. That's the first step. Ito, kukunin ko mula doon. Ito, kukunin ko mula doon. So, if I combine them together, using linearity, magiging isang 1 over h na lang yan lahat. Tapos, masusubtract f of t minus f of x. Do you get what I mean to say? Next, applying triangle inequality for integrals. Tapos, meron kong constant na 1 over h over there. Kaya may ganyan tayo. Do you follow? Okay, you can pause, no, kapag hindi kayo nakakasunod. Basta ulit, ito ay IF. I'm so sorry. Okay. The question is, how big is this integral? Well, dito na papasok yung continuity ni little f na ating ina-assume. Okay? Kasi yung quantity na to, if f is continuous, yung quantity na ito, where is that? Yung quantity na to can be, well, ma-estimate natin, as you will see. Let epsilon be greater than 0. Just like the 90% of the theorems in analysis, mga proofs nag-start sa let epsilon be greater than 0. Since f is continuous at x, by the definition of continuity, we can guarantee a number delta greater than 0, so that we can force f of t to be disclosed from f of x. Basta si t, pipiliin mo na malapit kay x. Did you understand that? Ulit. Because of the continuity of f at x, we can find a delta greater than 0 so that yung f of t, i-ensure mo na ang distance niya from f of x is less than epsilon over 2 as long as pipiliin mo si t in the domain so that it is of distance less than delta from x. Sa Tagalog, you can ensure that f of t is near f of x as long as you will choose t in the domain near from x. Okay, that's what you mean by the continuity at x. Now, di ba sa h yung nag-approach sa 0? Ganito natin sinasulat yun eh. Di ba sa math kapag may, lagay ko lang dito as a side note. Kapag may pinoprove kang ganito, definition yan ulit. Ayan, such that f of x minus L less than epsilon whenever, ganito yan eh. Diba? Oh, naging 8 delta yun ha. Ang h kasi natin ay nag-approach sa 0. Kaya parang ito ay h minus 0. Kaya ito yun. Ito yung f of x minus L. Okay? Okay, tingnan natin. Ngayon, kung yung h minus 0 has an absolute value less than delta, but greater than 0 because we don't allow h to become 0. We only let h as close as we want to 0. And t is between x and x plus h kasi kapag si h ay positive, may space sa pagitan ng x tsaka ng x plus absolute h. Kaya ako nilalagyan ng absolute yan kasi si h, ang katotohanan yan, pwedeng maging negative. Kung nandito si t sa gitna ng x at x plus h, how close is t from x? Well, yung distance nila, ulit, ganito na lang, positive na lang kunwari si h. Kasi pag negative naman, sa kaliwa ka lang naman, symmetric lang yon. Kung nandito kasi si t, how close is t from x? Ito yun. So, hindi yan aabot. H kasi ito eh. Di ba? Hindi yan lalagpas sa absolute value of h. But we have assumed that h is less than delta. Kaya ito ay totoo. So, i-apply ko yung continuity na nasa taas. Kapag ito ay totoo, how close are these from one another? Less than epsilon over 2. Kaya ito, as calculated in the previous slide, ito ay less than or equal to that. Tapos ito, according to the continuity, is less than epsilon over 2. You will have this. Constant na lang ngayon to. Upon calculation, ano nangyari? Again, ito kasi, ito kasi? Actually, dapat ito absolute h, pero pwede na rin. Yeah. Ang nangyayari, kasi ang integral ng constant, c times b minus a, no? So, parang in-apply ko yung formula na yan. Pag sinubtract ko to, that's h. Anyway, ang h naman, less than or equal naman sa absolute value of h. So, magka-cancel ito. May iwanan epsilon over 2. Well, epsilon over 2 is less than epsilon. So, it means to say that if h is small, this one is also small sa Tagalog. Therefore, ano na-prove natin? Ang derivative ni if at x is f of x. See? Let me just go back again to the statement of the second fundamental theorem para makita natin kung ano itsura niya. No? Meron akong gusto sabihin doon. Where is that? Hanapin ko lang ha. Ayan. No? Take note that this statement can be rewritten as shown. Kasi parang ito yung sa ganitong paraan, ito yung if of x kasi, di ba? Yung ganitong paraan kasi emphasizes the fact that if you differentiate something that you have integrated indefinitely or indefinitely, parang nagka-cancel yung derivative at saka yung integral. Parang that emphasizes the fact. Kaya sometimes this is something that you must remember. Okay? So let's go back to the current slide. So, meron ako example. Look at this. I have a function big F here, which is defined using indefinite integrals. Okay? Ano ba itong portion na ito? Actually, alam nyo gawin ito from calculus. Parang arctan yata ito, diba? So, it's going to be an arctan of x. Tapos ito may something na blah 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 blah. Pero assuming hindi nyo alam yun, you don't need to know. You are asked to show that this function is constant on the interval, on the positive side of the real number line. Pag sinabing constant, sabihin, kahit anong dalawang positive number ang ilagay ko sa x, laging parehas lang yung value nito, hindi nagbabago. How do we show that? Another way to show that is, well, to show that its derivative is 0 everywhere in the domain, in the interval. Naalala nyo yun? If a function has derivative 0 at every point in an interval dapat, then we can conclude that the function is constant there. Right? So, ang goal ko is to prove that this is constant by proving that its derivative at every point in this interval is 0. But first of all, is it really differentiable? Well, upon inspection, kasi continuous naman yung mga functions na ito sa interval na ito. So, by the second fundamental theorem, we are guaranteed that these two indefinite integrals are differentiable. Okay? So, what we're going to do is we pick an arbitrary point in this interval, let's say x. By the second fundamental theorem of calculus, ang derivative ng unang indefinite integral natin ay 1 over 1 plus x squared. Remember, yung t dun papalitan mo ng x kasi naka-x ka na. X na to. Derivative nito is now written in terms of x. Diba? From f of t, nagiging f of x yung nandun sa kanan. Kaya ako nga ni-recall yung itsura. Okay? That's the second fundamental theorem of calculus applied. Now, yung derivative naman nito, this is kind of tricky kasi hindi ito x. Sa second fundamental theorem, x to di ba? So, what we do here is we use the chain rule. Tatawagin natin u, yung 1 over x, take the derivative. Ayun yung derivative niya. So, yung derivative na ito, imagine niyo ano to, y. Itong buo, y. So, para kang meron dy dx. Ang dy dx, diba? dy du times du dx. Ito sa chain rule. Okay? Ang du dx mo ngayon ay negative 1 over x squared. Ang dy du mo ay ito. Ito ngayon, dito nag-apply yung FTC2 once again. Magiging 1 over 1 plus u squared. But what is u? U is 1 over x. Lalagay mo ngayon yung 1 over x dito. Ito si square mo, ganyan. Upon simplifying, ito yung lalabas dyan. You can just verify, ha? So therefore, ang derivative mo ay 0 for all x greater than 0. And that proves that f is constant on the interval from 0 to infinity. Try nyo lang, no? Halimbawa, kunin mo yung f of 100, kunin mo yung f of 200, f of 1 million, makikita nyo pare-parehas lang yung lalabas ng value dito. Nice, no? Now, one of the many corollaries of the fundamental theorem is, well, the change of variables theorem. Ang tawag nyo dito nung maliliit kayo sa basic na calculus, parang U substitution. But here, we are more fancy, kaya we call it the change of variables theorem. So here, you're given a differentiable function g, so that the derivative remains continuous on the interval AB. So it meant to say that g is continuously differentiable. Ganun yung term na sinasabi natin sa analysis. And then, let's say si f ay continuous doon sa range ng g. Kaya ako gustong gawin yun kasi I wanted to get the composition. I wanted to get f of g of x. Kaya ako nire-require na dapat continuous yung f sa g para yung composition mag-remain continuous. Sure tayo ngayon na ito yung function na ito ay continuous, therefore integrable. May integral siya. According to the theorem, equal to sa integral ng f of u du, nag-change ako ng variable. Pero yung limit ko nag-iba, naging g of a from g of b. Ano ba to? We will see. Ito yung ginagawa nyo dating mga tricks sa calculus. No? Kapag meron kang compound integrand like this, parang may f of u du, no? Nilalet mong u yung g of x. Tapos kinukuha mo yung du, right? Like so. Tapos ito ngayon, magiging ganon. Ngayon, para hindi ka na bumalik sa x, dahil definite integral naman ito, transform mo rin yung limits of integration. From a naging ua, from b naging ub, where ua is the value of g at a, and u is the value of g at b. Okay. So, anyway, mamaya may example, but let's try to prove. Now, first of all, meron akong gagamitin dito. Dahil si g ay continuous, by the extreme value theorem, ang domain niya kasi close interval from a to b, yung image ulit niyan ay bounded. May maximum, may minimum. Pero because of the what they call this, the intermediate value theorem, I can guarantee that the image is also a closed interval. Meron tong left endpoint, meron tong right endpoint, but it doesn't mean na ang left endpoint ay g of a at ang right endpoint ay b. No. Pwede kasing halimbawa, ibang picture. Let's say yung function mo is like this. So parang ito ngayon yung g of a, ito yung g of b, no? Ang image mo ito, yung buong interval na to. Actually, yung left endpoint ng g of ab yung minimum, ang right endpoint ng g of ab is the maximum. Hindi yun necessarily si g of a tsaka si g of b. Okay? For each x now, in the interval in the image of ab under g, which is also an interval, we can now define this. Now, take note, this is well defined kasi nga yung yung image ng ab under g is also an interval. You can integrate from g of a to any point x in that interval. You can integrate f, I mean, kasi si f is continuous on the range of g. So this is well defined. By ftc2, if you take the derivative of this indefinite integral at x, you get little f of x. Si g prime, continuous on AB. Itong composition na to, continuous din siya, kasi continuous si f sa range ng g. Ang product ng dalawang continuous na function ay continuous. And also, by chain rule, so by the way, kung continuous integrable na ha, by chain rule, if I take the derivative of this composition, ganito yun. And because the derivative of big F is little f, by the ftc2, mapapalitan itong big F ng little f, like so. So now, yung big F circle G, we mean to say na siya ay antiderivative ng function na to. So if I want to integrate this from a to b, anong mangyari? First, fundamental theorem, i-apply ko. Okay. Integral nito from a to b will be the value of f circle g, big F circle g, at b minus f circle g at a, which is written as follows. Pero, kung lalagay mo yung g of a dito, g of a to, parehas yun. So, this will be 0. Right? And if that is 0, wala na to. Ano yung f of g of b? G of b naman ito. Ito na nga. Finish na. Yun yung proof. Ito yung gusto natin ipakita. Anyway, this is just a formal statement of an already known fact from calculus, diba? So, no need to worry about this. But if you want to review again, you can pause and then rewind kung gusto nyo. Ina-apply ito sa mga functions like this, no? Ano ba ganyan? Paano nyo ginagawa ito? We normally let u be 2x plus 1 siya yung g of x. Okay? Tapos, kunin mo yung du, magiging 2dx. Kaya, ganyan. Para magkaroon ng 2dx yun, dadayain natin by putting a 1/2 outside. So, ito na yung f of g of x times g prime of x dx. Ayan na yun. So, by the change of variable theorem, papalitan mo lang ng u. Pero, don't forget to transform the variables para hindi ka nababalik ulit sa x. Ano yung g of 0? The value of u when x is 0 is 1. The value of u when x is 2 is 5. Kaya yan ganon. Ito naman, simpleng power formula lang yan. Therefore, we have the following. Alright? So, see you in the next lesson for another video lecture. Bye.